So section 10.1 is going to talk about conic sections. Conic sections are different values for A, B, C, D, and E when you plug them into equations like this. And you're going to get a variety of shapes depending on those particular values. Let's talk about some of those shapes and what you might see. First of all, it was some Greek genius millennia ago, thousands of years ago, who in his idle time says, you know what, hey, let's take two cones and put them tip to tip and then try and imagine what happens when you slice those cones. What kind of shape are you going to get with their intersection? And those shapes are your conic sections. They're a parabola when you slice parallel to one of the sides of the cone, a circle when you slice perpendicular to the axis of symmetry. If you tilt that plane a little bit, then you get a special oval called an ellipse, or you can get two parabolas that face away from each other, which is your hyperbola. You'll see these shapes in a lot of places. Now, one of the things that I'm not really going to go over very much, or actually at all in this section, is all the nuances of a parabola. This is something hopefully you saw in college algebra. There's this nice little point in a parabola called a focus, and that's opposite the directrix. A couple special points, both a distance of p away from the origin. But you'll see that shape all over the place. Suspension bridges. The cables here between the two main towers lie in a parabolic shaped arc. Newton used a parabola to create his telescope and also helped establish some of his theories about the theory of light. Radio telescopes are amazing. If you light a match, if you were to be able to light a match on the moon, they could spot the flare. That's just incredible. Where would you be if we couldn't do a parabola for Angry Birds, right? I mean, come on. All right. The Hubble Space Telescope. And this guy's, his name is Andrew Feustel. He's an OCC graduate. So when we say you can get anywhere from here, we mean it, right? Cool. Parabolic shaped reflector on the top of a building can draw in sunlight through a fiber optic cable into the middle of a building. How cool is that? That's some really neat technology, have actual sunlight in a building. If you're designing car headlights, you'd worry about the focus of your parabola. You want to focus and put your light source away from the focus, because if you put it right at the focus, then all the beams are going to come out parallel and form one dot on the road. So you need to spread it out. And where would we be without the grunts and groans provided to us by a parabolic mic? Monday Night Football just wouldn't be the same. So lots of applications for that. Ooh, my favorite, the vomit comet. They train astronauts this way. They have to get used to zero gravity. So they take these planes and they shoot them up at a really, really steep angle. And at the top of their flight, they trace out a parabolic shaped arc. And for a brief 20 or 30 seconds, you can experience weightlessness. So cool. And if you got $5,000, hey, your ticket can be next. Does anyone see something funny about this picture? Yeah, they got a cat here. That cat's got to be really unhappy, I would imagine. All right. Ellipse similarly has lots of properties that are useful, and you see them all over the place. Our planets in this solar system, and actually any solar system, will march around the sun in an elliptical shaped orbit. A lithotripter is amazing. It can help break up kidney stones and gallstones by using the properties of an ellipse. You put an electrode at one focus of an ellipse, and it's going to concentrate energy waves at the other focus, which is where hopefully you have your kidney stone or gallstone, and you don't have to operate. You don't have to cut you open. Whisper chambers. These are pretty cool. If you whisper into an elliptical shaped reflector from the focus, somebody at the other end of Science Center 5 in Lansing can hear you. And that other end is a long ways away. Do you see down here? So somebody over there can hear somebody whispering in this other one here. Hoffman transfers, elliptical shaped orbits. To get from one orbit to another, you have to go through another elliptical shaped orbit. And so on. Hyperbolas also have applications, nuclear cooling towers, Loran. I like them in architecture, and the Kobe Tower is really cool. Tons of applications. Hopefully a couple of them resonated with you a little bit. But our goal is, in this section, is to recognize what they are. And what they are is based on the form that you're going to see here. You know, what the values of A, B, and C are. So I'd like you to be able to establish or figure out, well, which conic section am I looking at? Just by looking at the equation without plugging this into Desmos or your graphing calculator. So let's take a look at some of the problems here, like number 52. And this is kind of like a decision tree. What you're going to decide when you work down these things as to whether or not something is a parabola or an ellipse or a hyperbola or a circle. So let's take a quick look at those. Starting with problem number 52. Okay, so we've got 4x squared minus y squared minus 4x minus 3 equals 0. Okay, so let's look at the first branch here. Is A or C 0? Basically, if A or C is 0, then there's only one squared term. If there's only one squared term, then your graph is a parabola. End of story. So that's pretty nice. Now, in this case, we happen to have two squared terms. So, okay, it's not a parabola. So let's go down to the next branch. Are A and C the same sign? Well, A and C are the coefficients of your squared terms. Do those coefficients have the same sign? No. So let me put in a few branches here for us. Is A or C 0? If the answer is yes, you're going to branch over to parabola. If the answer is no, you're going to go down here and ask yourself the next question. If A and C are the same sign, then we've got another question. If they're not the same sign, then it's a hyperbola. So what do you think here? This one's a hyperbola. And that's it. That's what I want you to be able to do. Understand what these graphs are. Now we'll go through in a little bit and graph a few ellipses, and I'll give you a quick refresher on graphing a hyperbola. But let's take a look at problem number 54. So y squared minus 4y equals x plus 5. If it's helpful to you, if you'd like to, you can move everything over to one side to get 0 on the right-hand side. If I did that here, that would be y squared minus 4y minus x minus 5 equals 0. And let's work through our little decision tree here. Starting back at the top, is A or C 0? In other words, is one of the squared terms equal to 0? Yeah, the x squared term is 0. So if that's true, then this is a parabola. Nice. Now there's two more here. Let me grab those out. Problem 56. 2 times x minus y, or 2x times x minus y equals y times 3 minus y minus 2x. Now this one we should probably clean up a little bit before we decide, what conic section it is. And by that I mean let's distribute the 2x and then get everything over to one side. I'll also distribute the y and do likewise. So 2x squared minus 2xy equals 3y minus y squared minus 2xy. If I try and move everything to the left-hand side, let me note for you first, 2xy, that the 2xy term is eventually going to cancel itself out, which is good, because those are really a pain to deal with. So 2x squared equals 3y minus y squared. And now let's bring everything over to the other side. 2x squared plus y squared minus 3y equals 0. All right. So we're going to need to play with that one. And let's look at one other one. You know what? I'll work on it with you. Why don't you see what you can conclude for this one first, and then we'll work on problem 58 together. Andrew? Can you show the chart again? Yes, yes, I can. So here's your chart.
I've got a question on 52. So the sides are opposite. Why do you call it a hyperbola, even though it says it's going to no?
Okay, let me take a look back at that. Oh, did I label these wrong? Let's see.
I think those are flip-flopped.
Yeah. Signs up. Yes, you're right. Thank you. So yes and no. Thank you. All right. So a little Photoshop here. Cool. Never happened. Thank you. All right. So let's take a look at this one. Maybe it helps to have the chart here as well. So first things first, is one of the squared terms equal to 0? No. You have a coefficient for each square term. So the answer is no. We'll branch over here. Are these opposite in sign? Again, no. So thanks, Andrew. We're following the correct branch on this one. So the last thing then is, are A and C equal? So are these coefficients of your squared terms equal? Does 2 equal 1? No. So if the answer is no here, then you've got an ellipse. And if the answer is yes, then what you're looking at is a circle. So just kind of depends on how this plays out. But it's nice to just be able to look at these things and know what the graph is going to be, even if you don't actually know exactly what it is. We know, generally speaking, what it is. So let's take a quick look at a graph like that, or let's say that actual graph. So 2x squared, let's try again. So 2x squared plus y squared minus 3y equals 0. How about a 0 here? There we go. So, an ellipse. Not bad. It's just as we predicted. The problem that you would face graphing this is, if you're trying to do this on your graphing calculator, you'd have to solve for y. It's not really easy to solve for y in a problem like this. you'd kind of be stuck a little bit. So, all right, are we okay with problem 56 here? Let's try problem number 58. So 9 times x plus 3 squared equals 36, minus 4 times y minus 2 squared. I'm going to start by moving a couple of these terms over to the left-hand side. 9 times x plus 3 squared plus 4 times y minus 2 squared. And what actually happens with the constant term, that 36, if I leave it on the right-hand side or not, doesn't really matter too much, because we're going to be basing our conclusions off of A and C. So, whatever happens to E, if I bring the 36 over or not, really is not going to make a difference. Now, let's try and save ourselves a little bit of work here. I'm not really interested in squaring this out, distributing, etc. I think I can kind of guess, if I did square this out and distribute the 9, what would be the coefficient of my x squared term? 9. It's going to be a 9x squared plus something. And then over here I'll have a 4y squared plus something. Doesn't matter exactly what that stuff is, right? We can still determine what shape this is. So, give that a shot. Take a look through here and try and decide, well, what conic section are you dealing with? All right, I think I need to print out a couple more here. Mimi, can you pass these around? See if we got enough. 2, 4, 6, 8, 10, 12, 14, 16, 18. No, that's not the one I wanted. Square. Okay. I think I noticed that one or two you might not have gotten a copy of that last one, so I'm just going to print out a couple extra here. All right, let's take a look at that last one and see what we can conclude. So coming back over here, we had a coefficient of 4 for the y squared term and 9 for the x squared term. So is A or C 0? No. Are they the same in sign? Let's see. Are A and C opposite in sign, I should say? No, they have the same sign. They're both positive. Are they equal? No. So again, it's an ellipse. So without graphing that, we can just look at that and know that it's an ellipse. Did we run out or do we have enough? Okay, good. So let's actually graph some ellipses, and we'll start with let me get one for you. Let's start with this one. This is problem 18 from a different book, so don't worry about it. It's also section 10.1. I just stole these from another class because it's going to be useful for us. Let's look at x squared over 9 plus y squared over 4 equals 1. So you can play with this and you can kind of look at it and realize that the coefficients of x squared and y squared are both positive but both different, and conclude that it's an ellipse. But what's the actual graph of this look like? Well, you could spend a little time plotting x and y intercepts on this graph. For instance, if you set x equal to 0, you'd end up with y is positive 2 or negative 2. Likewise, if you set y equal to 0 to get the x-intercepts, you'd end up with x equals 3 or negative 3. So you'd have those points, and then you could graph it, at least to try and get started. So let's take a look here. 0, 2, 0, negative 2, 3 and 0, and negative 3 and 0. Now you play a college-educated version of Connect the Dots. Something like that. Now I kind of sped this up from what I would do in a Math 1150 class, but we can speed it up without really losing too much. And that is, if you notice, there's a little connection between this equation and the vertices here, these points that I used to find my graph. And you can see that a little bit better if instead of writing this as x squared over 9, I wrote it as x squared over 3 squared plus y squared over 2 squared. And in this fashion, you can see how to find your vertices without actually setting x equals 0 and y equals 0. This distance away from the center is 2, and that corresponds to that 2 right underneath the denominator. And then likewise over here, you've got a 3. Well, the distance from the center to the vertices along the x direction is 3. So if you take the time to put it in this form, then it'll greatly speed up your graph of that equation. Nice. So let's see that again for a different one. And that is this one right here. 25 x squared plus 9y squared equals 225. Okay, well, there's a little problem. We don't have that in that nice form that I used just a minute ago. But it's not that hard to rewrite it and get it in that form. So let's spend a minute and try and tweak it, see if we can't get it in the right form. See if we can't get it looking something like that. Well, the first thing I would do is divide everything through by 225. I need to get 1 on the right-hand side. So 225, 225, 225, and success. I got 1 on the right-hand side. So I get 1 equals, now over here, I end up with x squared over 9 plus y squared over 25, because these cancel into the 225. There's one last thing that I would do. I'd write it as x squared over 3 squared plus y squared over 5 squared, and let that equal 1. So, kind of our last step here. From here, we should be able to graph this without too much sweat. The center of this is 0, 0. So in the x direction, how far do I have to move to find my vertices? In the x direction, 3 to the right and 3 to the left. How about in the y direction? Where'd I have to go? Yeah, go ahead. 5, up 5, and down 5. And then, as best as you can, try and draw a reasonable looking ellipse. Keep in mind they're smooth. And I hope I don't make anyone dizzy here. I'm just going to cheat. There we go. So there's our ellipse. Your ellipse has a major axis and a minor axis. The major axis is the longer of the two. Obviously the minor is the shorter of the two. Not bad. Not bad. Are we okay with these first two examples? All right. Let's go down here to problem number 26 and play around with this. What kind of a conic section are we looking at now? Take a look at your sheets. It's all right. Which one? Yeah, an ellipse, right? So these two are both positive. They're not equal, so it's going to be an ellipse. Now, exactly what kind of ellipse? Well, we're going to need a little help with this one. We're going to need to whip this one into shape, so kind of follow along. I'm going to do a process of completing the square, but I can only complete the square on something that has a coefficient of 1. So for these two terms, I'm going to factor out the coefficient of the x squared. So it's going to be 25 times x squared plus, what's left if I factor out a 25 from this? 2x. Notice you're not pulling out the GCF. The GCF will be 25x. You're just pulling out the coefficient of your squared term. So x squared plus 2x plus, let's put in a something here. And then we're going to do the same thing for the y squared and the y terms here. It's going to be 9 times y squared minus what? Good. 4y plus something equals 164. Okay. What I need to do now is complete the square inside the parentheses. Now, it's been a while since maybe you had to do this, so let me remind you on that trick. The trick is to take half of the middle coefficient and then square it. So half of the middle coefficient is half of 2, that's 1, and 1 squared is 1. And that's what's going to go right in here. So it's going to look like this. It's going to look like 25 times x squared plus 2x plus 1. And then we have to do the same thing for y squared. And I'm going to give you a chance to complete the square on the y squared. And we can kind of compare answers. So again, you take half of the middle coefficient, you get a number, and then you take that number and you square it. So whatever you get from here, you're going to square it. In this case, it's half of what? Negative 4. So half of negative 4 is negative 2. Negative 2 squared is 4 again. So let's put those numbers into our problem. So I'll put a 1 here and a 4 here. And that 4 is not showing up so good. Let me try and make it a little bit more clear. 4. But it's not really fair for me just to arbitrarily throw in a 1 here and a 4 here. It's changing the value of the left-hand side. So I have to keep things in balance. I have to do something to the right-hand side to keep it in check. So when I put a 1 here, I've really added not 1 to the left-hand side, but 25 times 1. So let's add 25 to the right-hand side to keep that in balance. How about over here? When I put the 4 here, what do I need to put here to keep the right-hand side in balance? 36. So this becomes 25 times x plus 1 squared plus 9. How does this factor now? Yeah, y minus 2 squared. Okay, getting closer. This is not in our standard form here yet. So what could I do to put it in my standard form? Divide by 225. So that's going to be 25 times x plus 1 squared over 225 plus 9 times y minus 2 squared. Again, over 225 is 225 divided by 225. I'll tell you what. We'll split the work here. I'll simplify the right-hand side. You simplify the left-hand side. All right, a couple of smiles at least. That's good. On the left-hand side, the 25 goes into 225, and the 9 goes into 225 nice and evenly. Let's just cut to the chase. This is going to be x plus 1 squared over 3 squared plus y minus 2 squared over what? 5 squared. Because 9 goes in there 25 times, or basically 5 squared. What's different about this one than our previous two? Yeah. The center is no longer at 0. Where do you think the center is? Somebody take a wild guess. Yeah, -1 and +2. So, yeah, I got another, this never happened. All right. So -1 and 2 is our center. Let's graph that. -1 and 2. I don't think this was, it might not have been problem 26. I just assumed it was, so maybe it wasn't. So -1 and 2 is up here. Now let's take a look at the graph. For the graph, I need to move a distance of 3 left and right. So 1, 2, 3, 1, 2, 3, and then up 5 and down 5. Good luck with that. It's going to be somewhere down here and up here, but you play the connect the dot game from there. Whoa. What happened? There we go. All right. So we're not going to actually be able to graph this one here. We could graph it with Desmos. Let's do that real quick, just to at least take a look at that. And we'll start out with, the cool thing about Desmos is that you don't have to have everything solved for. So 25x squared, then plus 50x, plus 9y squared, minus 36y. You know, it's not going to like those because those are capitals. Sorry about this. Plus 50x x plus 9y squared minus 36y equals 164. Okay. So at least it matches our expectations. Centered at -1 and 2. -1 and 2. There. Beautiful. Okay, are you comfortable with figuring out what kind of conic section you're dealing with and this process of completing the square? I know you only got one example like that, but I'm really, really, really hoping this is a review. Let's take a look at this last one here on the flip side of things. You should check at home that you can rewrite this as x squared, or this one can become this one over here. Check that at home. But let's do something else right now. What kind of a conic section is this? Hyperbola. You've got two square terms with opposite signs. This is as far as you have to go. Two square terms with opposite signs is a hyperbola. Now, once you write it in standard form, there's kind of a trick that you can use to graph these things. Again, you're going to struggle trying to graph this on a graphing calculator unless you get a little bit fancy. But if you're not going to do it on a graphing calculator, here's your best bet. Let's start out with the center of this. So where's the center, would you guess? Good. 1, negative 2. 1, negative 2. So that's down here. 1, negative 2. Now, for the moment, we're going to pretend that this is an ellipse. And if it was an ellipse, then I would need points to the right one and to the left one, and then up one and down one from the center. And now the trick is this. You're going to complete, it's called the parallelogram, or not the parallel, complete the rectangle here that would have these points on its side. Now this isn't your graph, and the next part's not your graph, but it helps you draw your graph. And what helps you draw the graph is when you draw the diagonals of this box, because the diagonals are going to serve as asymptotes for your hyperbola, here and here. If your squared term, if the x squared term is positive, it's going to open left and right. If the y squared term is positive, then it's going to open up and down. So if these were reversed, then I'd have something opening up and down as opposed to left and right. That's your graph. There's kind of a shortcut way that you can get the equations of the asymptotes. I could probably justify this mathematically, but it's something I just happen to notice. If you want the equation of these asymptotes, you can actually just replace 1 on the right-hand side by 0 and look at x minus 1 squared minus y plus 2 squared equals 0. If you now solve for y, you'll get the asymptotes. So if I move this to the other side, I get x minus 1 squared equals y plus 2 squared. Take the square root on both sides. Now on the left-hand side, I need to take plus or minus the square root. So it's going to be plus or minus x minus 1 equals y plus 2. If I move the 2 to the other side, I get negative 2 plus or minus x minus 1 equals y. And that's going to be the equation of my asymptote. You can clean it up a little bit from there if you want. It's not a problem. But that's the equation of each asymptote there. Okay, are you comfortable with your conic sections? I gave you a couple problems that you should try at home. This one, if you put it in the standard form, then it's going to look like this. And when you graph it, it'll look like this. So what I would suggest is that you copy this down and then solve it separately, and then come back and check your answer. And likewise with this one, when you put it in standard form, it's going to look like this, and its graph would look like this. You can also practice putting this one in standard form to be the same process. Okay, I'll go on 10.1. homework, uh, I'm just going to write this on the board. So let me get this stopped here, and then work on the homework in a minute.